In neuroscience, attention usually means the dynamic selection of a subset of inputs for more efficient processing. For example, people could easily pick up the voice of one person in a very noisy room. More generally, instead of hard selection of inputs, attention could be viewed as a reweighting or gating of incoming signal by a controllable weight. A lot of work on attention in neuroscience has been focused on vision system. According to the origin of the weight modulation, we can distinguish between bottom-up and top-down attention in the visual processing. One example of the bottom-up attention is the visual saliency map, in which the weights are calculated directly from visual inputs in the primary visual cortex, so the animal could attend to more attractive visual areas for later processing. In contrast, top-down attention, like spatial attention and feature attention, uses external cue signals like a location or color and shape features to control the weight modulation. Perceptual effects of attention are also closely linked with neural mechanisms of divisive normalization, which is an ubiquitous neural computation that a neuron's activity is normalized within a pool of neurons in order to reduce redundancy and energy consumption. It has been shown that divisive normalization models can explain a lot of attention effects. Another model related to gating and divisive normalization is the mixture of Gaussian scale mixture. As its building block, the Gaussian scale mixture is a simple probabilistic model describing the local variance dependency in natural image patches. When applied to an image patch, the GSM model infers a latent Gaussian variable from the image, and the neural activity is assumed to be proportional to the inferred Gaussian values. In addition to the original GSM, to model the interaction between a neuron with receptive field in the center of the image with some surrounding neurons, Pitkow and colleagues use a finite mixture of Gaussian scale mixtures to build a gated model for flexible divisive normalization. So if the image is homogeneous, the normalization is turned on. Otherwise, it is turned off. The predictions by MGSM model agrees with experiments in primate V1 errors. We can see that the concept of attention, gating, and divisive normalization are very closely related. In principle, the reweighting operation is a theory interaction between the signal, the weight, and the output. In this paper, we propose that using multiplicative theory interactions naturally gives a soft gating operation. And inference in this model generalizes flexible divisive normalization and provides a more extensible normalization motif with attentional modulation. In machine learning, attention is also a reweighting operation to evoke the gating in natural attentions. Although the specific form of the weight calculation has been evolved to accommodate billions of parameters like in transformers, the key component of gating, which is multiplication of an original signal by some weight, hasn't really changed. In order to see why theory interaction offers a soft attention operation, let's consider a simple XYZ as an energy term with some isotropic base measure. The figure here shows a contour of this density function. We can see that this simple motif describes a soft gating operation in which the value of one variable z controls the correlation between the other two. And this motif already exists in the GSM model that accounts for divisive normalization. Since the multiplicative theory interaction functions much like a continuous version of the transistor, we also call it statistical transistor. In general, we will define the whole model as a joint distribution with interaction terms up to third order. Without any constraint, the number of parameters is cubic in terms of the number of variables, making learning and inference hard. So in practice, we will use task-dependent graph structure to reduce the number of parameters. As a concrete example, here in this paper, we will reformulate the MGSM model for divisive normalization with our method and get similar neural predictions. Specifically, similar to the work by Pitkow and colleagues, we use GSM as our building block, which is shown in the black box. For visual clarity, in the figure, we only show the interaction between two GSM units, one corresponding to the center image patch, and the other corresponding to the vertical components at all surrounding locations. Instead of using a finite mixture, which could be hard to extend when the model gets larger, we build an NG-based model with only local interactions. Specifically, a new gate variable W is added to the model to control the correlation between two neighboring GSM units through theory interactions. When W is 0, both GSMs work independently. When W is very large, they will be more correlated since that corresponds to a lower energy state. So the whole model then is unified by theory interactions as shown in the graph. As a result, it's more generalizable and interpretable since the posterior of W can be interpreted as the correlation strength between two units. We train our model on natural image dataset with the elbow as the loss function. After the model is fit, we use Markov chain Monte Carlo as our inference method for accuracy. For comparison, we ran two grading experiments as in the MGSM work. Here are the illustrations for the stimuli used in these two experiments. We can see that our model with theory interactions give similar predictions as MGSM and also experimental recordings. So by performing inference in graphical models with three-way interactions, we provide a normative way to describe gating and divisive normalization, which are concepts closely related to attention in both neuroscience and machine learning. Our model could also be expanded to a grid of variables connected by theory interactions. And inference in this model may produce spatial attention and has the potential to provide interpretable neural computations involved in tasks like object segmentation. This is an important topic for future investigation, and with the advances in training methods for large energy-based models, it becomes feasible. Thank you.